Okay, so without further ado, let's start. So we will start as usual. We will do a recap of what we had done in the previous session. And so last time we looked at projective measurements, and we had seen that any projective measurement can be described by this projection operators, so P0 to Pn, and they have to follow some certain properties like Pi should be Hermitian, that is Pi dagger will be Pi, summation over Pi is identity, and also Pi squared equal to Pi. So if the operators follow this P0, P1 up to Pn follows these properties, then we can say that we have a projective measurement. And we also saw that if the projective operator corresponding to the pure state phi I is just get phi I outer product. And if we measure some state vector psi in the phi naught phi 1 basis, it gives us some projective operator acting on the psi with some normalization constant, which is given by this, and with some probability mod phi naught psi whole squared, and here inner product of phi 1 psi mod squared. So, and the main thing that we started the last time was the concept of mixed states. And we saw that if the system is a statistical ensemble of some pure states like here phi naught, phi 1 up to phi n, then we can write a density matrix like this, which is rho, which is like P naught outer product psi naught, P1, psi 1, psi 1, and so on up to Pn psi n psi. And of course, the probabilities should add up to 1. And this we called as the density matrix. So this is the density matrix for a mixed state. So for a pure state, what will happen? Okay, only one probability will be 1. The other probabilities will be 0. So for example, the pure state for psi naught will be just get psi naught, outer product. And we also looked at the Born rule for density matrix. So we saw that if I have a density matrix rho and if I'm measuring it in the phi naught phi 1 basis, then the probability that we will get phi naught will be just trace of rho multiplied by the projection operator of phi naught, and that is just phi naught outer product. And similarly, we got the probability of getting phi 1 when we were measuring in phi naught phi 1 basis. And we looked at some of the properties of the density matrix, and we saw that all these properties arose from physical constraints. So the fact that probabilities are real meant that rho, the density matrix rho, has to be Hermitian. The fact that probabilities are non-negative, that led to the fact that they have to be positive semi-definite, that is, the eigenvalues will be non-negative. And the fact that total probability is 1 led to the rule that trace of rho is 1. And if we apply these constraints, these three constraints on the density matrix, then we can write it in this form. We had seen last time, we had derived it. Okay, it would be like I plus x sigma x plus y sigma y plus z sigma z divided by the factor of 2. And this expression x sigma x y sigma y plus z sigma z, we saw that that could be represented as r dot sigma. So basically, you could write rho as I plus r dot sigma whole divided by 2. But there was one additional constraint that the mod r has to be less than equal to 1, or in other words, x squared plus y squared plus z squared is less than equal to 1. And we had concluded the session by asking that what is the physical significance of this? So what does this mean? The fact that we can represent a density matrix rho in this form. Okay, so what does this mean? And so, yeah, would any of you like to take a guess? Admittedly, there are less people today, so okay. So let me give you the answer. The fact that we can write rho like this, like in the form of I plus r dot sigma by 2, where this holds. Try to see one thing that we are able to express this complex density matrix with only taking this x, y, z, these three real numbers as parameters. So basically, uh, in order to fully, because you see, identity sigma x, sigma y, sigma z are like constants; they are not going to change. The only parameters which you can tune are x, y, and z, which follows a certain relation. So of course, since these are real numbers, so x, y, z is a member of the real space R3. Okay, so you can see that using three real numbers, let me write it down for you. So x, y, z, you are able to describe a complex density matrix. Or in other words, from this you can conclude that the density matrix rho can be represented in by a vector in R3. X, Y, Z in R3. Okay. Now, one thing notice that this cannot be any vector in R3. The vector has to satisfy the constraint that x square plus y square plus z square less than equal to 1, which means that uh, so what does this mean? This means that they should lie within a sphere of radius 1, because you see x squared plus y squared plus z squared is nothing but r squared, where r is the distance of the point from the origin. So basically, if you have these coordinates, the real coordinates, let's say, so x, y, and z, then basically within, if this is a sphere of radius 1, r equal to 1, then the density matrix will be represented by a point inside the sphere. Okay, because as you have seen, x squared plus y squared plus z squared, this is less than equal to 1. Okay, so r squared was less than equal to 1, which means that r is less than equal to 1. So, and this is exactly, so if you remember that we had also represented the state vectors on a Bloch sphere, but they were on the surface of the Bloch sphere. Here we are saying that the density matrices can be on the surface or inside the Bloch sphere. Okay. And so, as you might have guessed, all the pure states lie on the surface of the Bloch sphere, because the pure states can be uh, described by density matrix, by the state vectors. Pure states lie on surface, and the mixed states lie inside the Bloch sphere. And in fact, this is something that you can prove, because you see, like, how do you write the density matrix for a pure state? So rho is like psi psi. So the for a pure state, the density matrix is also a projector. So for rho squared equal to rho for pure state. And if you take rho to be of this form, I plus r dot sigma by 2, then you can prove from the fact that rho squared equal to rho that mod r will be equal to 1. So I'll leave you to do that. So for the people who have joined in just now, let me recap what we have done briefly. Is that we had ended the last class with the question key: if you can express rho in this form, I plus r dot sigma divided by 2, then what is the significance? And here mod r was less than equal to 1. So basically x square plus y square plus z square is less than equal to 1. So we concluded that with only 3 real numbers, we were able to so 3 numbers x, y, z, we were able to describe a complex density matrix. Or in other words, the density matrix can be represented as a vector in R3, which follows this condition. And this condition means nothing but the fact that the density matrix has to lie inside the Bloch sphere. Okay. And for pure states, I have like given you the information that the pure states lie on the surface of the Bloch sphere, while mixed states lie inside the Bloch sphere. Okay. Now, let's say we take two states, two density matrices. And let's say they are density matrices corresponding to pure states. Let's say psi psi. And of course, it can be written in the form, let's say 1 plus r1 dot sigma divided by 2. And rho 2 will be phi phi. And this would be I plus r2 dot sigma by 2. So if that is the case, then on the density matrix, and of course, since these are pure states, so they lie on the surface of the Bloch sphere, that is mod r is 1, mod r2 is also 1. Now, let's try to represent them on the Bloch sphere. So let's say it is this vector r1 vector. So this is a point on the surface, r1 vector. And let's say we have another point on the surface like this. Okay. Now let's take a third density matrix, which is like, so these are how we have defined rho 1 and rho 2. So let's say we take the rho, which is alpha rho 1 plus beta rho. So basically alpha and beta are the probabilities of getting the pure states rho 1 and rho 2. So, and of course, because of that, alpha plus beta has to be 1. Okay. Now, if we put in the value of rho 1, so what is rho 1? It's nothing but I plus r1 dot sigma by 2 plus beta, and here rho 2 is nothing but I plus r2 dot sigma divided by 2. So what does this give us? So if you take look at the coefficients of I, this is nothing but alpha plus beta I by 2. And so if you look at the coefficients of sigma, then it is just alpha R1 vector plus beta R2 vector dot sigma divided by 2. Okay. So basically, we can, here alpha plus beta, as we have said, is 1. So this is nothing but I by 2. So let take 2 in the denominator plus alpha R1 vector plus beta R2 vector dot sigma. Okay. And you see, so when we basically take a mixed state from these pure states rho 1 and rho 2, what happens is that my this R vector changes. So for rho 1 it was R1, for rho 2 it was R2. For rho we are getting alpha R1 plus beta R. So let's try to think about how this would look like. So you have, say, R1 here, let's say R2 here, and you want to find out what alpha R1 plus beta R2 would look like given that alpha plus beta equal to 1. So in order to understand that, let's look at a similar example which happens in classical mechanics. Okay. So suppose you have a ball of mass m1 and a ball of mass m2, another ball of mass m2. Its position is r1 and its position is r2. So how do you calculate the center of mass of these two balls? So you just say that this is m1 r1 vector plus m2 r2 vector divided by m1 plus m2. So you can, so basically you can of course write it like this. And you can assume that this is alpha and this is beta because you see again alpha plus beta equal to 1. And as you know from classical mechanics that RCOM will lie on the line joining M1 and M2. So RCOM would lie here. And it would divide, and if you see, it would divide it in the ratio, this line in the ratio, M1 is to M2, or in the ratio alpha is to beta. So similar thing will happen here. If you take alpha R1 plus beta R2, then it will lie on the line joining the tips of R1 and R2. And it would also divide it in the ratio alpha is to beta. Because you see alpha R1, so alpha would be on the side of R1, beta will be on the side of R. Now, if we look at this on the Bloch sphere, will we get? So you join R1 and R2, and then here it would be R vector, which is like alpha R1 plus alpha beta R2 will basically be a point inside the Bloch sphere, and it will lie on the line joining R1 and R2 such that this is divided in the ratio alpha is to beta. Okay. Is this thing clear? Till now, is there any questions or queries? So the conclusion from this is that if you have like a vector which is denoting the density matrix rho 1 and another vector which is denoting the density matrix rho 2, and if you have some rho which is alpha rho 1 plus beta rho 2 like this, then the point representing rho will lie on the line joining this r1 and r2 vectors and it will divide that line in the ratio alpha is to beta. So that's the conclusion. So now let's look at a special case. Question. Oh, what is the significance of the identity matrix then? The significance of the identity matrix. Okay, we will look at that. Okay, what is the significance of the identity matrix? So, okay, let's try to answer that question. So we have this row I plus R dot sigma, right? By 2. Now, if you put R vector equal to 0, okay, what will you get? I by 2. So basically, the center of the Bloch sphere is I by 2. And so that is that represents a completely mixed state, and we will come to that. Okay, why it is a completely mixed state. This is a completely mixed state, or rather maximally mixed state. Sorry. So that is the significance of I. So is that clear, or was this the question, or were you asking something else? Okay, okay. All right. Now let's look at a special case. So let's say this like we have taken row psi psi and row 1 psi psi and row 2 phi phi. Okay. And now let's take that psi and phi are orthogonal. All right. So in that case, what will happen? So if you have the Bloch sphere, then we know that the orthogonal states lie on the antipodal points of the Bloch sphere. So let's say if psi is here, then phi will be somewhere here. Okay. And then if you take, say, rho alpha psi psi plus beta phi phi, it will again here it will be some point in between, so that it divides these lines joining these 2 points in the ratio alpha is to beta. Okay. And but notice one thing, that we could have also written it as the combination of some other pure states. For example, let's say I take this and this, such that this point is dividing this line in the ratio alpha dashed and beta dashed. And let's say this is psi dashed and this is phi dashed. Okay, so you can also write rho in terms of alpha dashed, psi dashed plus beta dashed, phi dashed. So in general, there can be an infinite number of representations of rho. So in general, infinite number of representations are possible. Because you see, you can draw another line, say from here to here, and you can represent rho in that form. But for this point, for this particular row that we have taken, which is not at the center, we can show that there is only one, like there's a unique representation in orthogonal, in terms of orthogonal states. So there's a unique orthogonal representation. Okay. Now, so this is for a state which is not at the center of the Bloch sphere. Now, as I had mentioned while answering Rajrupa's question, that the center of the Bloch sphere is I by 2. Okay. Now, here, how can you represent it? So this is at the center. So let's say I draw this line. Okay. So let's say psi uh, phi, where psi and phi are orthogonal. So of course, the center will divide the diameter in a ratio 1:1, right? If it is in the ratio 1:1, then how will the density matrix look like? It would be like say half psi psi plus half phi phi. And actually, if you see that I have drawn it along the z-axis, so this is nothing but ket 0, this is nothing but ket 1. So basically, you can write it as half 0 0 plus half 1 1. Okay. And in fact, if you take any diameter, so basically connecting any two pair of antipodal points or orthogonal states, so then it can be, let's say, phi and, or let's say chi and chi prime, chi bar, then you can write it as half chi chi plus half chi bar chi. Okay. So it is, you can see, and all of this will equate to I by 2. So this I by 2 is a spatial state. So because it does not have a unique orthogonal representation, it has infinite number of orthogonal representations also. And you see, and in some sense, and it is maximally mixed in the sense that everything can be, if you take half and half of any two orthogonal pure states, and if you mix them, then you get I by 2. So that's why it's called a maximally mixed state. Okay, so now let me ask you something. Let's say I have this, I have a point inside the Bloch sphere. So this is my point, and it divides the line joining orthogonal states chi bar and chi in the ratio 4:1. So what is this? So this is representing the matrix rho. So can you guess what this rho will be? And also till here, if you have any questions, you can ask. Okay, so Rajrupa says that it would be alpha chi chi plus some beta chi tilde chi tilde. Now, can you find out the values of alpha and beta? That is right, but what will be alpha and beta? Oh, by the way, this is 4. 4:1. Okay, the ratio is 4:1. Okay, so Rajrupa is saying that beta will be 1 and alpha will be 4. But you see, alpha plus beta has to be 1 because what are these? Alpha is the probability of that the ensemble is in chi, and beta is the probability that it is in chi bar, right? So the alpha and beta are probabilities, so they should add up to 1. So having said that, what should be the value of alpha and beta? Alpha will be 4 by 5 and beta will be 1 by 5. So finally, the density matrix will be 4 by 5 chi chi outer product plus 1 by 5 chi bar out. So hopefully with this example, uh, your this should be clear how you can find out the point in the density matrix when you like the point on the Bloch sphere which represents the density matrix, given that you know how to like given that you know what ratio that it divides, or if you know the density matrix, how to you can represent it on the Bloch sphere. So you can now go both ways. All right. So uh, let's now look at how the density matrices evolve. So the unitary evolution of density matrices. So let's recall once how pure states evolve. Okay. So for pure states, if you remember that if you have some psi at t equal to 0, and if you apply some unitary, then you could find out psi at t equal to t, let's say. So you just acted the vector by a unitary. That's all you had to do. So what will happen for the density matrix? So we have to find out how rho, which is like psi t outer product evolves. So we have to find out how bra psi t evolves, for example. So from here, if you take the dagger, so psi t dagger will be u acting on psi 0 whole dagger. Or if you take the dagger inside, then the order will change. So u dagger, and you will have psi 0, kid psi 0 dagger. Now, kid psi t dagger, as we have seen a lot of times, is just bra psi t. And here you have u dagger, and kit psi 0 dagger is again bra psi 0. Okay. Now, what is rho-t? Rho-t is just psi t outer product. And kit psi t, you see, is just u acting on psi 0. So this would be u acting on psi 0. And bra psi t will just be psi 0 and u dagger acting on it from the right hand side. And what is this? Psi 0, psi 0 outer product? This is nothing but rho 0. So u rho 0 u dagger. So this is how density matrix will evolve under a unitary. So you will act with the unitary u from the left hand side, you would act with the unitary u dagger from the right hand side, and you would find what rho t is. And also remember that here the evolution was given by the Schrodinger equation, right? So IH cross d psi dt is H psi, H acting on psi. So this was the uh, uh, Schrodinger equation, which told us what the unitary would be. Okay. And in a similar way, you can show that for the density, for the for rho, for the density matrix, or any general density matrix, it is given by IH cross d rho dt, and there's a commutator which is H rho acting, just simply this. Okay, so what is a commutator? Commutator of two operators is simply this is H. So AB commutator is AB minus BA. And remember, since these are matrices, so they may not commute. AB might not be equal to BA, so generally they will not be zero in general. Okay. All right. So any questions till now, till here? And you can, although I have shown this for a pure state, so I have taken a psi-t, which is the density matrix for a pure state. You can take a mixed state in general, and because if you take linear combinations here, like alpha psi-t plus beta chi-t, even then you would see that this rho t will be like this. So basically, this relation will still hold. So, any questions? Okay. So if not, then there's another very interesting thing that we can observe. So if you take the Bloch sphere, so now since we have uh, mixed states also, so the points can lie inside of the Bloch sphere also right now. So remember, when we did for pure states, we said that unitaries rotate the Bloch vector by some angle, about some axis, right? If you represent them on a Bloch sphere, so unitaries rotate Bloch vector by some angle chi about some angle, some axis n rho. And if you remember, that unitary which does this is just given by exponential minus I chi by 2 sigma n, where sigma n was sigma dot n. Okay. Now, so we made this statement for pure states which lied on the surface of the Bloch sphere. But this is in general true for any state inside the Bloch sphere also. So basically, if you have a state which is inside the Bloch sphere, so for this r is less than 1, then it will also be rotated. So if you draw a smaller sphere here, so by acting unitaries on this state, let's say rho, you can go to any point on this subshell of radius of this fixed radius r less than. Okay, because rotations cannot change the uh, the length of the vector. So in other words, we can say that if, let's say, there are rho 1, rho 2, such that the corresponding uh, vectors, the Bloch vectors representing them, let's say R1, R2. So if R1 mod R1 equal to mod R2, then you can go from rho 1 to rho 2 with a unitary. All right. Or in other words, so you can also say that rho 1 and rho 2 are unitarily connected. So, so what I'm trying to say is that two points on the Bloch sphere will be unitarily connected if they're at the same distance from the origin. Okay, so for example, if you want to go from, let's say, a pure state, let me draw the sphere. I guess this is more or less drawing is not that good, but okay. So yeah, let's say you want to go from this state psi, which is on the surface of the Bloch sphere, to I by 2. So are these two states, so psi is the density matrix corresponding to this. So do you think that psi and I by 2 are unitarily connected? So can you, with the help of a unitary, can you go from psi to I by 2? Any ideas? No. Why not? Because they are at different distances from the origin. So I by 2 is itself the origin. So basically for I by 2, the r vector is nothing but the null vector theta. For this pure state psi, mod r vector will be 1. And for this mod r vector is c. So they are at different distances from the origin, so they are not unitarily connected. Okay. Uh, all right. Now let's look at how we can measure density matrices. So, or how we can describe the measurement of density matrices. So, measurement. For pure states, we already saw in last class what will happen. Uh, Okay, so we saw that for pure states or state vectors in particular. So if you have a system in QIQT psi, you would get something like the projective operator acting on psi with a normalization, which will actually give you this phi naught here and phi 1 here after measurement, if you're measuring phi naught, phi 1 basis. So what is the corresponding thing for density matrices? So you would have rho, and then you would do the same thing. Say you're measuring in this basis, then the probability, if you remember the Born rule for density matrices, the probability will be of getting phi naught, for example, will be trace of rho the times the projection operator corresponding to phi naught. Okay, and of phi 1 would be probability trace of rho multiplied by p phi 1. And this would be uh, p naught rho p naught, and there will be a normalization factor of trace of p naught rho, and this there would be p1 rho p1 divided by trace of p naught rho. All right, so basically if you calculate, this is equal to the trace of P naught rho P naught. So basically you are having P naught rho P naught divided by trace of P naught rho P naught, because remember our normalization condition is now trace of rho, like the trace of the density matrix should be 1, because that is what now defines my total probability, the trace. So that's why we divide it by the trace of itself, so that the trace of the whole thing becomes 1. Okay. So now let's look at the measurement problem again. So let's say I have the Bloch sphere again, and my system is in the state I by 2. Okay. And so what will happen when I measure I by 2? Say I am measuring in QIQT0, QIQT1 basis. Measure in, okay. So after measurement, it will either go to QIQT0 or it will go to QIQT1. So in both the cases, you see that the length of the block vector is not preserved. So initially the length of the block vector is 0, and then it goes to something which has a length 1. So either QIQT0 or QIQT1. So in other words, this is not a rotation. So the measurement process is not a rotation of the block vector. And from which we can conclude that the measurement is not a unitary operation. So this is another way of arguing that measurements cannot be described by unitaries. So till here, is there any question? Okay, so if not, let's move on to the next topic, which is, and the last topic that we will look at is the reduced density matrix. So let's go back to the system of 2 qubits. So if there are 2 qubits, you know that the Hilbert space would be the tensor product of the Hilbert space of the individual qubits. So C2 tensor C2, like that. So basically you have 2 qubits here. Let's say Alice. So let's name them qubit A and qubit B. And we saw that in such a case, the total state of the system could be entangled. So for example, it could be in some state like this, 0A tensor 0B plus 1A tensor 1B, right? And we saw that this cannot be written in the form psi tensor phi. And so we called it an entangled state, which is not a product state. Now, let's ask the question, what is the, so of course we know, okay, let's ask the question first and then we will see. So what is the state of qubit A? So one thing is for sure is that since it cannot be written in this form like psi tensor phi, then the state of the qubit A is not a pure state. Okay, so this is not pure state. So now the question is that then is it a mixed state? So let's try to look at that. So for psi AB, we can write the density matrix. So what will it be? It will just be psi AB outer product. Okay. And so this is, so I'm just getting rid of the tensor product sign. So 0A, 0B plus 1A, 1B by root 2. And here outer product with 0A, 0B plus 1A, 1B by root 2. Okay. So now we will have 2 here, and we will have 4 terms on multiplication. So 0A, 0B, and I'll quickly write it for you guys. 0B, and then we will have something like this. Right, and okay, there will be more terms, so let me so here we will have 1A, 1B, 0A, AB, AB. Okay, so we will get this rather long expression. Now, how can we simplify this? So one thing that you have to note is that if I have this IA tensor JB, and we outer product this with, let's say, kit KA tensor kit LB, then what will happen? So you see, I have taken a state which is a state of the composite system I tensor J, and then outer product with the kit of that system. So in order to calculate this, what you can do is that you can take the outer product of system A first. So corresponding to system A, you have kit I and kit K. So kit I, kit K, A, and you will have here, if you now do for system B, it would be like J, B, L. Okay, this outer product. And so let's use this fact here. Let's try to do that. So here you will have 0, 0, A, and 0, 0, B, plus here it will be 0A, 1A. So 0, 1 outer product of A, and then 0, 1 outer product of B, 1, 0 outer product of A, 1, 0 outer product of B. And similarly for the last term. So yeah, bear with me, it's a long calculation, I know, but the end result will be interesting. Okay, so this is what we get. Now, in order to find what the subsystem A is, so in order to find the state of qubit A, you just take a partial trace. So take we will see what that means. Partial trace over qubit B. Okay, so let's see what that means. So basically we have row AB, and from there I want to find the state of A, which is nothing but row A. Okay, so I am saying that row A, the state of qubit A is trace over B. So I am not taking, remember, okay, by the way, trace is, what was trace? In general, trace was the sum of diagonal elements. So the sum of diagonal elements of a matrix. Okay, now trace of B, if I take trace over B of row AB, so what that would mean is that I will leave 0, 0 of qubit A unchanged, and I would take a trace over 0, 0 of B. So this would be like, so 0, 0, A. So A is unchanged. Now I take trace of 0, 0. So hopefully this transformation is clear. So I am taking partial trace over B. I am not taking the trace over A. Okay. And similarly, you can do it for the other ones. So which will give you 0, 1, A, trace over 0, 1, B. So notice again A is unchanged. And then we have 1, 0, A, trace of 1, 0, B. Okay. And then 1, 1, A, trace of 1, 1, B. All right. Now, let's try to, so we have to calculate. So trace is the trace over B here is nothing the sum of the diagonal elements of this matrix, which is 0, 0 outer product. Okay. Now, if you, and we have to find the trace of these and this and this. So these four traces, if I find out, then I would be able to find out rho of A. So let's try to do that. So what is 0, 0 is nothing but this 1, 0, 0. So if you take trace of 0, 0, you would get, so sum of diagonal elements will be 1 plus 0, which is 1. And similarly for 0, 1, it would be like 0, 1, 0, 0, trace of this, you see, what will it be? So diagonal elements are 0 and 0. So this would be 0 plus 0, so 0. Similarly, 1, 0, if you take the trace, you will find that this is 0. And trace of 1 outer product 1, if you find, it will be 1. So here, this trace value is 1, this trace value is 1, this trace value is 0, this trace value is 0. So since this is multiplication by 0, these two terms will disappear. Okay, and we will be left with, by the way, there was a division by 2 which I missed. So let me just add it in. Okay, so basically this would be the whole divided by 2. So we will only have 0, 0 term and 1, 1 outer product term. So rho A is just 0, 0 outer product A plus 1, 1 outer product A by 2. So basically half 0, 0 plus half 1, 1. So we see that we started with a pure state, this entangled state psi AB. This was pure state. Okay, the composite system was in a pure state. But when we are looking at the subsystem A, then that subsystem A is no longer pure. This becomes a mixed state. And in fact, if we again locate it on the Bloch sphere, so you see, this is 0, 0, and this is 1, 1, the North Pole and South Pole. And this would, this row would divide it in the ratio half is to half or 1 is to 1. That is, this is nothing but the center of the Bloch sphere, or this is I by 2. If you calculate, so 0, 0 is 1, 0, 0, 0, and here if you do 1, 1, then there will be a 1 here. So On adding, you will get I by 2. All right. So, in fact, you not only get the mixed state, but you get the maximally mixed state. And since the subsystem of this entangled state is a maximally mixed state, we see that the pure state is maximally entangled. Okay, so this psi AB, uh, so this is maximally entangled. All right. So any questions about this entire thing? Is this clear? And also if you take this rho B, if you calculate, that is trace over A, rho AB, then again this would again be I by 2. Okay. So any questions so far? Like, is this understandable? Like, did you guys understand this? Yes, no, anything? Okay. All right. So now, so yeah, we saw that if the entangled state is, so if it is a maximally entangled state, then we will get maximally mixed. So I'll just give you an example where, uh, like what happens if I take, say, a non-maximally entangled state. So let's say I take this psi AB as 1 by root 3, let's say 0, 0 plus root 2 by root 3, 1. Okay. So I'll leave you to do the calculation. So find row AB. Okay. And then you can find row A just in the same way that I had done. You can just trace out the subsystem B. So trace over B row AB and you will find that this is something like, so I did the calculation beforehand. I'm just telling you the result. So it would be 1/3 0 0 plus 2/3 1 1. And this, if you locate on the Bloch sphere, this would be like, so this is 0 0, this is 1 1, and so it would be a point which would divide this line in the ratio 1:2. So basically some point like this. Okay, so this ratio would be 1:2. Let me write it this way. So 1 on the side of 0 0 and uh, 2 on the side of 1. All right, so this is the ratio. So as you can see that this is not a maximally mixed state. So if you start with a not a maximally mixed state. So if you start with a non-maximally entangled state, you would end up with a non-maximally mixed state. Okay. And of course, if you have a separable state, what will happen? So that is very trivial. So let's say 0 0 plus 0 1 by root 2. So you can of course take 0 common out in the tensor product, of course, remember, and then 0 plus 1 by root. And of course, in that case, each subsystem is known trivially, like you don't have to do the uh, density matrix, reduced density matrix stuff. So both of them will be pure states if it is separate. The subsystems will be pure. Okay, so for product states. So in conclusion, you can see that density matrices can arise mainly in two ways. So one way is that if you have an ensemble where you have different pure states with different probabilities, and in that case, you can have a density matrix or a mixed state description. And the other case where you can have a mixed state is when the system is a subsystem of some entangled state. Okay. So, yeah. So, any questions till here? Okay. If not, so we will end our discussion here. So, this is all I wanted to tell you about density matrices. So, unfortunately, we won't be able to cover the next topics, which I had previously said that I would cover, namely Bell non-locality and different quantum communication protocols like teleportation and superdense coding. So I'll give you some references from which you can study. So just a second. Uh, yeah, so there's a review on Bell non-locality by Brunner. So for non-locality, you can study uh, so the name of the paper is Bell non-locality and the author is Nicholas. So the first author is Nicholas Brunner. Uh, sorry. Okay. And so this is one reference that you can look at. Let me also give you the archive number. So the archive number of this paper is 1303.2849. Okay, so this is something you can look at for non-locality. Also, there's a video, let me on YouTube, which kind of helped me learn about non-locality better. So let me see if I can share this with you. Just hold on a second. Um, There's a question in the chat. So Rajrupa is asking ki, is the density, is the matrix denoted by a point? Yeah, that's exactly right. So, and the beauty of the formalism is that you're able to do it because density, the matrix is not just any matrix, it's a density matrix which follows certain criteria. So those three criteria that I had described, and that helps us to denote the matrix by a point. Okay. So yeah, that's exactly right. We are able to denote the matrix by a point. Yeah, and if you think about it, it might initially mind-boggling to you, but yeah, that's actually the fact. Okay, so I am sharing the YouTube link. Yeah, so I have shared with you a YouTube link. You can, like, in order to learn about Bell non-locality and the EPR paradox, you can look at that video and also read this paper by Brunner. Okay, this archive paper, and hopefully that will give you a good idea about non-locality. And for the quantum teleportation, super dense coding, and QKD, you can just simply look at Nielsen and Shaw. So, uh, and when you're learning quantum teleportation, make sure that you know about the no cloning theorem. Okay, and yeah, so I think that's about it. And of course, please also look at the various other algorithms. So in our sessions, we had discussed the Deutsch algorithm, so which was the simplest algorithm. So please have a look at the other algorithms, especially quantum Fourier transform, uh, Schwartz algorithm, and so on. Okay, and Grover search also. These are some of the very important algorithms. Grover's algorithm. Okay, so that's about it. So if you have any questions on what we did today, or since this is the last class, last session, so if you have any questions on anything throughout the course of these sessions, you can ask now. Or if it is, even if it is anything which we have not covered but you want to know about or something like that, you can also ask that. Entanglements, Superposition and interference is the best. Yeah, you can say that. And in fact, entanglement, uh, rather than entanglement, I would say that non-locality and superposition are what leads to advantages in all these quantum algorithms and communication protocols. Okay, so that basically, yeah, so non-locality is manifested in the form of entanglement, that is for sure. So yeah, you can say that entanglement, superposition, and interference, they are the basis. Yeah, and although interference you can also have in classical mechanics, yeah, so quantum mechanics is not necessary for that. So I would say entanglement and superposition is the best. Also duality, wave particle nature. Um, yeah, like that is duality is a consequence of you can say quantum mechanics, but that really so wave particle duality is rarely useful for quantum information. Okay, it's interesting in itself, but it's not so. In general, it's not that useful for quantum information. Yeah, that's true. Yeah, that is true. Yes. Yeah, it started with the double slit experiment. So basically, people realized that they can do double slit experiment on the electrons and they would still have the similar kind of probability distributions on the screen. And yeah, so it started with a double slit experiment. And of course, quantum mechanics, I think, yeah, started with, yeah, you can say double slit experiment, but also, let's say, photoelectric effect and things like that. Yes. Yeah, so Karthik says that yeah, it's quantum mechanics is not deterministic, but it's probabilistic in nature. But you have to understand that classical mechanics can also be probabilistic. For example, when you are looking at statistical mechanics, that's a probabilistic theory. But the fact that it is not deterministic is more ingrained in quantum mechanics than it is in classical mechanics. Okay. So if you remember, we had talked about subjective and objective uncertainty. So subjective uncertainty or subjective ignorance rather. So subjective ignorance can lead to probabilities and subjective ignorance is there in classical mechanics, but objective ignorance is not there in classical mechanics. So objective ignorance is only there in quantum mechanics where you have superposition. Okay, so yeah, Kamal would like to. Uh, Before that, I would like to thank you guys for sticking around and doing all this, going through all the tutorial sessions. And yeah, it means a lot to all of us. And okay, and Kamal would like to give the closing statement to the conference. Yeah, you're welcome, Karthik. And of course, if you guys have any questions or if you would like to get in touch later on, you can email me. You guys have my email ID. So yeah, so with that, I would hand it over to Kamal for the closing statements to the conference.